Alright, moving a little faster ahead, we have the glomerular filtration rate, which is around 125 milliliters per minute or 180 liters per day. Males are going to have a slightly faster filtration rate, and that's usually due to the filtration coefficient. And then we have the total amount of filtrate produced equals to around 50 to 60 times the amount of blood in the body. So 99% of the filtrate is reabsorbed since you only 1 to 2 liter urine excreted per day. So the amount of fluid that leaves through here, only about 1% of it actually becomes urine. Everything else is reabsorbed back. So if the glomerular filtration rate is too high, fluid flows through the renal tubules too rapidly for them to reabsorb the usual amount of water and solutes. Urine output rises, chance of dehydration, and electrolyte depletion. If the GFR is too low, wastes are going to be reabsorbed and azotemia may occur. And azotemia is the presence of urea in blood. If glomerular filtration rate is controlled by adjusting glomerular blood pressure from moment to moment. Glomerular filtration rate control is achieved by three homeostatic mechanisms. We have renal autoregulation, sympathetic control, and then hormonal control. The first one, the renal autoregulation, is the ability of the nephron to adjust their own blood flow and GFR without external nervous or hormonal control. We have there's two mechanisms through which it does that. First one is myogenic mechanism, and the second is tubulo-glomerular feedback. So the first one is simple. It just means myogenic mechanism. So any smooth muscle, when it's being stretched, it wants to shrink back. It tightens up, it constricts. So when there's too much blood flow in here, then your kidneys are going to sense that it's too high. Your kidneys are going to sense that. I'm sorry. So you have your afferent arteriole coming in. If there's too much pressure and it stretches, then the arteriole itself is going to constrict, supposed to normalize the amount of pressure. So that's the myogenic control. And then we'll just so we read everything. Increased arterial blood pressure stretches the afferent arteriole, and arteriole constricts and prevents blood flow into the glomerulus from changing much. When blood pressure falls, the afferent arteriole is going to relax and allow more blood to flow through the glomerulus, so that filtration remains stable. Then we have the tubulo-glomerular feedback. Mechanism by which glomerulus receives feedback on the status of the downstream tubular fluid and adjusts filtration to regulate the composition of the fluid, stabilize its own performance, and compensate for fluctuation in systematic blood pressure. So juxtaglomerular apparatus. It's a complex structure found at the very end of the nephron loop, where it has just re-entered the renal cortex. Loop comes into contact with the afferent and efferent arterioles at the vascular pole of the renal corpuscle. It's gonna make sense in just a sec. So, the nephron loop. So, this is the convoluted tubule. It leaves, goes down, and with the loop Henle, and then it comes back with the proximal convoluted tubule is going to be the close one, and then distal convoluted tubule is going to be this part right here. And this part, when it comes back, it's going to it's going to contact the afferent and the efferent vessels. So they have these things called the macula densa. So the closest part to the afferent and efferent is going to have these cells that are macula densa that are sensitive to sodium and other electrolytes, mostly sodium. So what they're going to do is the macula densa are going to realize that there is a lot of sodium here, and if there's a lot of sodium here, there's a lot of urine here. If there's too much filtration going on, the macula densa is going to be sending in hormonal, well, it's paracrines. It's not strict hormone because they don't go through the blood vessels. It leads through the interstitial space, so it's called paracrine. So these paracrine cells are going to be sending a message out to the mesangial cells, and the juxtaglomerular cells. And what the juxtaglomerular cells is going to do is going to tighten up the afferent arteriole. So if the afferent arteriole is smaller, then a little less blood is going to go through here, and if less blood goes through here, the glomerular filtration rate is going to go down because of the lesser pressure that's available in here. That's going to be pushing the filtration out. So also the sympathetic nerve fiber does the same exact mechanisms by squeezing the juxtaglomerular cells. The other thing it does is the mesangial cells are going to be adding pressure on the capillaries with inside. So if they're adding the pressure inside, that's going to reduce the size of the capillaries, reduce the amount of blood flow, and if GFR is also going to go down. So if the GFR falls, as in if there's not enough of it, then the macula relaxes afferent arterioles, that's this one right here, and mesangial cells, which is the ones inside. Blood flow increases and glomerular filtration rate rises back to normal. The renal autoregulation maintains a dynamic equilibrium. GFR fluctuates within a narrow limit only. Blood pressure changes do affect GFR and urine output somewhat. Renal autoregulation cannot compensate for extreme blood pressure variations. Over a mean arterial pressure range of 90 to 180 millimeters of mercury, the glomerular filtration rate remains quite stable. Below 70 millimeters of mercury, the glomerular filtration rate and urine output ceases. It ceases because if there's only 70 up here, then by the time it gets down here, it's going to be around 40 or 30. If it's that low, no matter how much this constricts, no matter how much the afferent arteriole is going to constrict, it's not going to be enough to overcome the 32 millimeters of mercury here and the 18 here. So there's not going to be any net output. Everything that leaks through here is going to be leaking right back in. So there's not going to be any net filtration pressure, and no urine is going to be formed. So it occurs in hypovolemic shock. Hypovolemic shock, your heart rate goes up, your blood pressure goes down. If your blood pressure goes down past the 70 millimeters of mercury in terms of mean arterial pressure, then no urine is going to be formed. So if here's the negative feedback control. If there's high glomerular filtration rate, then the macular densa is going to sense it, and it's going to change in the rapid flow of filtrated renal tubule sensed by macular densa. It secretes those little hormones, which is paracrines, and the paracrine secretion is going to constrict the afferent arteriole, and it's also going to be through those mesangial cells. It's also going to be constricting the capillary bed, and that's going to result in lower glomerular filtration rate or lower urine production. Sympathetic nerve fibers richly innervate the renal blood vessels. Sympathetic nervous system adrenal epinephrine constrict the afferent arterioles in strenuous exercise or acute conditions like circulatory shock. So if there is other needs in your body, like your skeletal muscles are going to need more blood, then your sympathetic nervous system is going to constrict the afferent arteriole, which is going to reduce pressure. So once you squeeze the afferent arteriole, it does two things. The first thing it does is it reduces the amount of blood flow, so more blood is going to be circulated throughout your system. The second thing it does is it reduces the amount of pressure inside the glomerulus. So even though your afferent arteriole could squeeze and function even when there is not enough blood pressure, the reduced blood pressure is going to produce lowered urine output. So here's the ROS system. The ROS system is going to be renin, angiotensin, aldosterone mechanism. Aldosterone we're going to cover later, but the first two part is going to be the liver always produces angiotensinogen. So angiotensinogen is a normal protein that just circulates in the blood in its inactive form. So when you do feel the a drop in blood pressure, your kidneys secrete renin. And actually, specifically, the juxtaglomerular cells are going to be these cells right here, are the ones that secretes the renin. And when it secretes renin, it secretes when there is not enough urine production here, then it secretes the renin. So once the blood comes out, if there's not enough of it, then it senses that the blood pressure must also be low, and so it sends out the renin. Renin goes in. Renin is basically an enzyme and converts angiotensinogen, which is a 453 amino acid long molecule, to around a 10 amino acid chain of protein. From there, we have the ACE angiotensin converting enzyme that is mostly found in your lungs, but it's found all throughout your body, even in your smooth muscles of your blood vessels and everywhere else. So ACE converts the angiotensin 1 to angiotensin 2. Angiotensin 2 has a, a large number of functions. Like if it travels through the brain and through the hypothalamus is going to activate the thirst and drinking mechanisms, where your hypothalamus is going to tell your brain, your conscious awareness, to drink more water. And also, what it does is it secretes aldosterone. It doesn't secrete aldosterone. It secretes antidiuretic hormone. And Also in your kidneys, it secretes aldosterone. Aldosterone we're going to cover later, but aldosterone preserves water. Antidiuretic hormone, antidiuretic hormone. So anti, as in no, it prevents diarrhea. It prevents urination. It doesn't prevent urination. It absorbs more water. And the other thing it does, the main thing it does, is increases blood pressure. So if there is more blood pressure, then your organs could get the amount of blood that it actually needs. And then all of these is going to be leading to elevated blood pressure. So just reading all of these things, we have renin secreted by juxtaglomerular cells. If BPU drops dramatically, renin converts angiotensinogen, a blood protein, into an angiotensin 1. In the lungs and kidneys, angiotensin converting enzyme, or ACE, converts angiotensin 1 to angiotensin 2, the active hormone. Oh, it's also the thing is that the angiotensinogen, there are other mechanisms where angiotensin could bypass all of these and just become angiotensin 2, or if angiotensin 1 could become angiotensin 2. So any of these mechanisms from angiotensin to angiotensin 2 could take place without either renin or ACE. We have angiotensin 2 is a potent vasoconstrictor, raising the blood pressure throughout the body. Angiotensin 2 constricts efferent arterioles, raising glomerular filtration rate despite low blood pressure. So angiotensin 2, if the blood is really low and the blood pressure is also too low, then it constricts the efferent arterioles so that it can increase the corpuscle inside the corpuscle capillary bed. Inside that, it could increase the blood pressure regardless, even if there is not enough coming through the afferent arteriole. So it lowers blood pressure in peritubular capillaries, enhancing reabsorption of NaCl and H2O. So it does this. This is actually really so complicated thing. So what it does is, since there's the peritubular capillaries that we looked at much earlier on, so there's two of them. The first one is this one, cortical nephron, and then juxtamedullary nephron. So the efferent arteriole is going to be going through here, and the efferent arteriole for this part, which is about 85% of the stuff, is going to be leaving through here. So if there is not enough blood coming through here, that means it's going to have lowered blood pressure. In any arteriole, when there's not enough blood pressure, it's going to have the amount of the amount of pressure that's pushing up against the endothelial cells of the blood, it's going to be lowered. If that's low, then the interstitial fluid has more of a way to get into the capillaries. So whatever sodium and water is in here in either the interstitial space or the tubules, is going to be absorbed back into the capillary bed of the peritubular capillaries. So that's the mechanism that the kidneys use to increase blood pressure. So angiotensin 2 stimulates the adrenal cortex to secrete aldosterone and promoting sodium and H2O reabsorption in the distal convoluted tube and the collecting duct.